Yeah, okay. So, um, hi everyone, welcome on board. This is the continuation of series 2 of the hydrogen group webinar series. And we've been having some of these throughout the year, particularly the upper half of the year. And we'll be having a few of these going on, going the next 1 year, 12 months, once a month, a presentation each. So today's topic is on insight into the new electrocatalytic materials for production of hydrogen. And with us is Carlos Fernandez, our very own, from Robert Gordon University, and he'll be talking us through these materials and probably their use in hydrogen. Carlos is originally from University of Hull, where he did his PhD in electrochemistry, electrocatalytic reactions, and currently a senior lecturer in bioanalytic chemistry at Robert Gordon University. Welcome on board, everyone, and I hope Carlos, equally welcome, and please do get started in the presentation when you're ready.
Thank you so much, James. Thank you so much, everyone, for coming today to the presentation. So today I will talk to you, as James was mentioning, insight into the new electrocatalytic materials for the production of hydrogen. So first of all, I'm going to give you an overview of history of some of the elements which are key for our lives, for our materials. Also some definition of electrochemical terms, what HER and OER reaction means, and why hydrogen, and how is hydrogen produced, and some of the electrocatalytic materials. So first of all, we have surrounded by 4 beauties of life. This is something that was published from Life between 1883 and 1972. So it's a particular interesting magazine that was, and some the main 4 elements, which are carbon, hydrogen, oxygen, and nitrogen. So hydrogen, as you can see, is something that has been interesting to all of us for a long, long time. So hydrogen is the main atom for water, for acid, bases, gas, oil, coal, etc. So why it's electrochemistry? So it's a study of chemical processes that causes electrons to move, and some of the study of the redox reaction, reduction, oxidation processes. So we have here an electrochemical cell. So the most important aspect of the electrochemical cells, as you can see, we have some electrodes. So in this particular case, will be an anode and a cathode. Anode usually is oxidation and cathode reduction. We have a solution, and we have electrolytes, and that usually will be a salt and will be some type of potential charge to help the reaction to start. 2 half reaction will occur, one at an anode and one at the cathode. So we have what we call an cell, but in fairness, it's just 2 separate reactions, as you can see. So electrocatalytic or electrocatalysis is what it is. So an electrocatalyst is a catalyst that increases the rate of the reaction on an oxidation or reduction reactions in an electrochemical cell. So here, for example, I put an example of reducing agent and oxidize, and what an electrocatalyst will do to the reaction. So we're going to see examples in a minute. Some of the factors that affect an electrocatalytic material will be the nature of electrocatalytic particles. We will see materials, size, shape, and surface structure. This is something that we're going to look at and see based on different graphs in a minute. Will be also the nature of the support, which is the material, surface structure, and electron transfer properties. And we'll have an important aspect, which is the interaction between the catalytic particles and the support material. The properties of an electrocatalyst will be activity, stability, and selectivity. So those are the main aspects that we're going to be looking at. And some more in particular, one will be quantitatively the current density is generated and how fast the reaction is taking place for a given applied potential. The relationship is described with the Tafel equation. So this is going to be looking at the rate of an electrochemical reaction to the overpotential. So one of the interesting reactions that we are interested, all of us at the moment, is the electrolysis of water. What it means, electrolysis is coming from Greek, so lysis, it means a breaking, and electro is just applying a particular current. So this is something that is a water splitting into oxygen and hydrogen. Hydrogen gas is something that all of us now we are familiar, as we see every day. Hydrogen gas can be used as a hydrogen fuel or remixed with oxygen to create, again, an oxyhydrogen gas, which is used in welding and other applications. So there are two types of reaction on the electrolysis of water. One is the OER, or oxygen evolution reaction, and the other one is the HER, or hydrogen evolution reaction. The oxygen evolution reaction, as you can see, we have two water, then oxygen, 4 protons and 4 electrons. So this is what we call the complementary anodic half reaction. So basically we said earlier on, the electrochemical cell has two parts. One is the anodic, when the oxidation takes part, and another the cathodic, when the reduction takes part, usually in electrochemical water splitting. We require 4 proton and electron transfer per oxygen molecule. The oxygen evolution reaction is the more complex of the two half reaction and is consequently responsible for the majority of inefficiency in electrolysis devices. So that is a key aspect when we try to develop an electrolyzer in the future. Also, one of the interesting aspects of the oxygen evolution reaction is the limiting reaction in the process of generating molecule oxygen through chemical reaction. But it's not just all bad for the oxygen evolution reaction. Developing improved catalysts for the OER is the key to the advancement of a number of renewable energies, and in particular solar fuels and metal air batteries, which I am also interested. So this is something that we did last year. So we use different material to create an electrocatalytic system. So in this particular case, we have used zirconium site on graphene using a ball milling and solid solution acid pyrolysis method. So this is just a system in which, as I mentioned, we just created the zirconium, nitrogen, oxygen, carbon here on the graphene substrate. This is something that we're going to explain in a minute more in detail why those process works in this way. So the hydrogen evolution reaction is the production of hydrogen through the process of water electrolysis. As we mentioned earlier on, the water electrolysis produces hydrogen and oxygen throughout two reactions, hydrogen evolution reaction and oxygen evolution reaction. The evolution of hydrogen is possibly limited and based on the dissolving of molecules coming from the cathode's surface. So again, this is important. So as you can see, slowly, we're introducing the importance of catalyst materials. So in the hydrogen evolution reaction, we have 2 protons plus 2 electrons giving the hydrogen. It's the cathodic reaction. Remember, the other one, the oxygen evolution reaction, was the anodic reaction in the electrochemically water splitting or electrolysis. The HER is a classic example of a 2-electron transfer reaction with 1 catalytic intermediate and offers the potential to produce hydrogen. So as you can see, the catalyst is important to minimize the overpotential necessary to drive the HER. So catalysts are key for our reactions. So what are the good properties of a catalyst? So we need to have an optimal hydrogen absorption energy. This is a prerequisite. And also hydrogen absorption, desorption behaviors of catalysts are crucial for the development of active HER catalysts. As I mentioned earlier on, we put, for example, graphene as a substrate due to being a porous material and the absorption desorption systems. So the next step is where can we find hydrogen? So here on Earth, we said it's a vast number of hydrogen atoms are contained in water, plants, animals, and of course humans. So that's the slide that I put at the beginning related to life, where the four main elements, carbon, hydrogen, oxygen, and nitrogen, were described. It is a very scarce as a gas, so we have less than 1 part per million by volume. So they are quite interesting properties. And where is it also coming from? So it's coming from, for example, solar panels, solar power, wind power, or water power. This is coming to, we need that to start the electrolysis system of water, creating hydrogen, as I mentioned there, and water, and producing electricity or energy to generate fuel cells. So that's the key aspect. Hydrogen production, as you can see, this is quite a very interesting paper from 2021. So in here, it just mentioned the production of hydrogen and also the main process in where hydrogen is produced. So as you can see, the main two processes or where hydrogen is produced is the steam reforming of methane, so a liquid fuel and natural gas. This is the only one of the main problems is the emission of CO2 with unstable supply. At the moment, this is one of the best or more efficient system where we have a 74 to 85% production. The other systems which are quite interesting is a water electrolysis. So this is some of the advantages. We have no carbon footprint. So this is obviously fantastic, eco-friendly, less energy, and oxygen as the second product. But the problem with here is the storage and shipping problem and applicable for specific purposes. That's one of the reasons why one of the best carriers for hydrogen will be ammonia. We have also other methods like a wind energy, nuclear or solar, where the efficiencies are considerably quite low. Nuclear energy, again, is a carbon-free and sustainable energy issue, which produce 45 to 50% in terms of efficiency. Depends, the problem with that type of energy depends on mining and processing of uranium and some of the policies related to obviously nuclear plant, as well as obviously some accident that has happened over the years. The other one, as I mentioned, is gasification of solid fuel, so 60 to 75%. The inconsistent production of hydrogen because of the feedstock, a generation of heavy oils and formation of tar. This is obviously the disadvantage of that particular method. As you can see, I have also put the prices here. So at the moment, we have hydrogen production cost US dollar per kilogram. So 227 to 10.30, which is the water electrolysis. And one of the key aspects on the water electrolysis we'll talk in a minute is about the catalyst. So we are moving on into some of the hydrogen basics. So some of the hydrogen, so it's the universe's most common and simplest element, consisting of one proton and one electron, can be produced from fossil fuel-based feedstocks. This is something we mentioned earlier on. Can be produced from off-peak electricity. We mentioned nuclear, solar, wind, tidal, biomass, etc. And can store energy produced by renewable energy technologies. One of the examples we mentioned earlier on, one of the carriers will be, for example, ammonia or methane. Okay. So as you can see, hydrogen is already in our life. It has been our life for a few years now. So this is hydrogen buses in Aberdeen. So as you can see, it's powered by hydrogen. So it's zero emissions. So in theory, it looks something absolutely fantastic and amazing, but we're going to see some of the disadvantages in a minute. There is also a hydrogen project in Aberdeen. So as you can see, this is the hydrogen facility. And you can see from the picture, this is in Dykes Road. So as you can see, this is one of the initiatives that the city is moving towards reduction of CO2, which is obviously a fantastic idea. Okay, so far, one of the things is we're going to produce energy from water. It seemed for me very clever idea, creating that from water. So this is, I'm guessing, is something that has been only with us for a few years. It must be, I'm guessing. Well, unfortunately, no. The fuel cell history, it comes, as you can see, from that particular slide, it coming from the art library in London, so Royal Institution in London. So this particular gentleman is Sir William Robert Grove, and he's one of the first pioneers on the fuel cells. The fuel cells that he developed into the fuel cells that we are currently seeing are quite similar. In particular, already knew that the best catalyst was platinum. So as you can see on the left-hand side of the slide, we're neutral, and we have some platinum electrodes. So as you can see, they were splitting of water into hydrogen and oxygen. And hydrogen and oxygen were trapped in different tubes. Another gentleman, quite important, is Christian Friedrich Chauvin. So that is again from 1799 to 1868. So that was an interesting experiment the gentleman did. And one of the things that we can see in the middle of the on the slide that I said electrolysis, is just we're starting to see the introduction of a stack fuel cell. Okay, so he had already in his mind, due to the combination of series and parallel, that the combination of stacks will be able to increase the current and the voltage. Okay, so this is already had a visionary thing about the fuel cells, and we'll see in a minute how similar they are on respect of that. So as you can see, this is the fuel cell, so it's very similar to what Chauvin and Sir William Grove visioned at that time in 19th century. So you can see we have a system, a pile stacks with oxidation and reduction. Okay, so can we see we have a system where you have hydrogen coming in and the oxygen, and then production the water electrolysis. Yes, they have an idea. You see now the fuel cells, what they have is a stack different cells together, and that's the idea is to increase efficiency, okay, as well as energy. Okay, so one of the things, this is coming from the UK Energy in Brief 2021, is published. So one of the things we said, hydrogen can be produced from a variety of sources, as we have already seen. For example, so natural gas, nuclear power, biogas, and also solar and wind. One of the challenges is harnessing hydrogen as a gas on a larger scale to fuel our homes and businesses. We're going to see why. Okay, and one of the reasons, as already I mentioned in the fuel cell history, is the catalyst. So in the UK, 85% of homes and 40% of the country's electricity currently relies on gas. In the US, it's 47% of the household rely on natural gas and 36% on electricity. So it's still very high values. One of the things about natural gas, it just produce, produce methane. So methane is the main constituent of the natural gas from oil and gas field. Natural gas is a readily available resource and cost effective. It's a cleaner alternative to coal. So this is something quite interesting and good. However, as you can see here, but when natural gas is burned, then provides heat energy and also our friends, CO2, okay, so and water. So this is the main product. So, okay, so what we have mentioned so far, we mentioned about electrodes, electrolysis of water, some electrocatalysts, and some of the hydrogen evolution reaction, and some of the oxygen evolution reaction, and some examples. So in the slides before, I mentioned about fuel cell, and I mentioned about the history of fuel cell, and I mentioned about the pioneers, Sir William Grove, and also Schoenwein, about using platinum. Okay, so why they use platinum? So this is a representation of an ideal hydrogen evolution reaction electrocatalyst. We should possess hydrogen absorption energies approaching delta G equal to 0. So as you can see, when we approach to 0, the best materials is platinum, it's rhenium, it's palladium, it's iridium, it's rhodium, cobalt, nickel, wolframium, molybdenum, niobium, copper, gold, and silver. Okay, so those are the most powerful electrocatalysts, as we can see, and this is depend obviously on the energies, as I mentioned earlier on. But all those elements are, I can't even remember the name. All the elements are in, oh yes, critical raw materials. So what are critical raw materials? So there are materials that are critically important to key economic sectors, which are platinum, rhodium, iridium, nickel, cobalt, rhenium. Okay, let's investigate each of those. So if we go to the British Geological Survey, so this is a website where it's giving you, offers you the production of the mines of all the important materials. Unfortunately, it has only 17, 18, 19, 20, and 21. So 22 is not available yet. But we can have an idea. So cobalt. So as you can see, we have the tones of the cobalt, metal content, and the countries which produce cobalt. We have the main producer of cobalt is Congo, so Democratic Republic of Congo. Okay? As you can see, is the massive producer. So in the world total, so for example, in 2021, the world total was 131,000 tons, and only Congo mined 93,000. So that is obviously more than a very high percentage of the total amount of the world. Also, the other one that is produced quite a lot of cobalt, as you can see, is China, Canada, Russia, and Australia. Okay, so those are the main producers. So I'm guessing in Congo, the way it's mined cobalt, it will be with the best technology in the world, office for every single person that is working on the mines, beautiful, extremely good conditions, and so on. So let's see. Oh, I was wrong again. So this is a mine of cobalt in Republic of Congo. As you can see, the conditions are not the one I thought. okay, with air conditioning, offices, very good salaries, etc. So this is something obviously important to consider. This is again some of the kids and young age, every single person in Congo trying to extract cobalt for us to come into other countries and to say that we are green. Yeah, we are. So that is where cobalt comes from. Okay, so there are two interesting books. One of them is Cobalt Red. I highly recommend both of them. It's How the Blood of the Congo Powers Our Lives. And the other one, which is quite interesting also, is a Bolt Rush. So you can see, I have one of the books in here with me. So those are very interesting because it's telling us about how our transformation or conversion into green is affecting other countries. But why love is abundant elements. So I love rhenium. That was another material. Wow, I thought it was more than that. Oh my goodness. Okay, so a tons metric. So Poland 11, so 9 in 2021, and Chile 29 tons in 2021. So rhenium, which is another lovely catalyst, seems to be very scarce. Okay, let's carry on. So platinum, I love platinum. Beautiful metal. Okay, so platinum, some advantages. So very effective for hydrogen evolution reaction, water splitting. History told us already, the father of the fuel cells, Sir William Grove, and also Svensson, were able to use already platinum. Okay, so it is a fantastic electrocatalyst. But the problem is very high. As our friends from ABBA will say, money, money, money. So the active sites are only located on the surface of the catalyst particles. So that is quite important to understand. So, okay. So this is just platinum and the group metals. So it's the main production of platinum and group metals. As you can see in the previous slides, when I was mentioning, everything was based on tons. Now we are changing. We're going a little bit smaller, kilograms. Okay. So as you can see, one of the main reasons is, apart from the price, is the scarcity. Okay, so we don't have much on Earth, platinum. So where platinum is coming from? It's coming from South Africa. As you can see, this is the other beautiful catalyst that we have, palladium. Again, talking in kilograms. So rhenium, already cobalt. We talk about platinum now and palladium. So all the four important catalysts, as you can see, has some adversities in that way. So palladium, platinum. So in South Africa is the one, as you can see from the numbers, the main producer. So platinum is producing in 2021 141,626 kilograms, and palladium is also producing 84,000. Other platinum metals, where we mentioned earlier on, which are important catalysts, producing 59,000. So that is the main. We have also main production in Zimbabwe, as well as Russia. So Zimbabwe is also producing 14,732 kilograms, 12,619 of platinum and palladium, another metal 3,195, and Russia producing 21,000 kilograms of platinum and 85,000 kilograms of platinum per year, as we mentioned here. So as you can see, one of the main issues that we're finding already is just the metals, which are the electrocatalyst or the catalyst, platinum, palladium. We have seen already rhenium, cobalt. Then they have some issues. So I wanted to show you also the map of the critical raw materials around the world. Okay, so what are them? The materials that are critical, and as you can see, iridium is one of them. Palladium, as I mentioned, platinum, rhodium, ruthenium, cobalt. We also mentioned, it doesn't appear in here. Don't know why. Palladium or nickel. Okay. So as you can see, those are what we call the critical raw materials. They are important to our are important and key for the transition of greener energies. So what can we do? So that is the question now we need to ask ourselves. So as we mentioned already, we are using critical raw materials. The systems are going to be extremely expensive. Okay, and also it will have a duration of time very low, because obviously we are mining those elements from the earth and they are not going to be forever. Okay, so that is something we also need to think about. So what we can do is create nanoparticles. So what are nanoparticles? So the idea is basically creating or downsizing the catalyst to single atoms. It is highly desirable to maximize efficiency by using nearly all platinum atoms. So that is one way. So rather than using the platinum electrodes that in history in the 19th century were used, the idea is just to use nanoparticles. Okay. Reduce also the loading amount of platinum. So the idea is to create a bimetallic system. So having, let's say, platinum with another metal. Also by adding carbon. Okay, so compound as a support. So support carbon quite porous. So it's for the absorption, desorption in catalyst will be interesting. A carbon material can be precisely controlled to obtain a desirable nanostructure with high specific surface area. Carbon-based materials, this is something I will mention. So for example, graphite, if we go again into the mines, it comes in the most and the producer of graphite, one of the biggest producers is China. Okay, so producing this year we're producing about 800,000 tons compared to other countries only of 50 and 70,000 tons. So that is also something we need to consider. Okay, any more advantages? So the substrate enhanced electrical conductivity allows fast electron transfer for hydrogen evolution reaction. The superior catalytic activity can be induced by the strong interaction and synergistic effect of the metallic species and the carbon supports. So this is something basically what we were saying earlier on, this bimetallic effect that platinum and another metal of that critical raw material that we mentioned would have an effect on. So we're going to just now looking at some interesting articles that have been published over the years. So some work that we have done, as well as something that obviously other colleagues have done. So this is in 2016, colleagues did they use a platinum single atom and cluster catalysis of the hydrogen evolution reaction. So in this particular system, what they do is using a platinum precursor with, we mentioned, carbon or nitrogen dopant sites to create a system. Okay, so that particular system will help for the hydrogen evolution reaction. So they used as I mentioned earlier on, carbon is very important, and one of the systems they used in here was nitrogen dope graphene nanoseeds. Okay, so this is another type of material. Again, one of the problems with graphene is quite expensive. So we take the alternative of platinum, adding nitrogen and another carbon-based material, which obviously work really well as an electrocatalyst. As you can see here, platinum compared to the platinum nanographene. But the problem again is the price. Okay, it's the cost. The other system, every system is very similar. So I'm trying to reduce the amount of, as I mentioned, platinum and substituting with different nanoparticles or other type of materials. Or as I mentioned earlier on, OB metallic system. So in this particular case, they're using platinum and nickel. Okay, so with platinum nanowires and single atomic nickel species on ultrafine platinum nanowires. And again, a fantastic system. As you can see, this is just cyclic thermograms showing the effectivity of that particular system. The other one, quite interesting, again, using platinum and another element, which is a ruthenium, again, another type of inexpensive alternative to platinum here. So a ruthenium with carbon and nitrogen. Okay, so this is something quite interesting piece of work, because here platinum has not been used. So in this case, that particular composite or system of carbon nitrogen framework serves as a versatile platform and the absorption, nucleation, and growth of ruthenium nanoparticles. Okay, so that's the idea. And the idea would be provides abundant coordination site for the distribution of ruthenium in the nanoparticles and in the layers. The other one we have mentioned, and they were on the list or on the figure that I was showing you, is the iridium and wolframium or tungsten. Okay, so that is another interesting aspect, another publication quite interesting that is looking at those absorption for the splitting electrocatalysis of water. The other one, another system they use here is a bimetallic platinum and copper with a carbon nanofiber. So in this particular case, again, another type of system, quite interesting and quite giving very interesting properties. They used some system like electrospinning and graphitization technique to encapsulate platinum and copper. That at the moment is difficult to commercialize that, but at least there is some ideas in order to reduce, as I mentioned earlier on, the platinum and other type of materials. They found an excellent hydrogen evolution reaction performance, and this is attributed, as I mentioned earlier on, synergetic interaction between the platinum and copper or the bimetallic system. The uniform distribution of the alloy nanoparticle and the use of carbon nitrogen with 3D architectures. Another system here used cobalt. Cobalt, as I mentioned earlier on, is coming from mainly Republic of Congo. So anyway, so cobalt here, they use, and also graphene. So this is again very interesting publication and very interesting system to the production of hydrogen evolution reaction. However, this is again, I doubt it will be commercialized in the future. So they have excellent performance as electrocatalyst and other interesting aspects. The other one, another interesting one, is using graphene oxide template to generate tantalum and nitrogen. Okay, so this is a 3-step system. As you can see, we have the graphene oxide, then you have a hydrolysis, calcination, and nitridation to obtain the nanomeshes. They form a 2D tantalum oxide layer, which one then convert into the desired product during the final nitridation step, and the highly crystalline structure of the nanomasses matches that of the bulk of the titanium. The thallium, sorry. Another system, again, if you remember, this is molybdenum selenium system, was also mentioned into the one of the best catalyst or electrocatalyst. Okay, so we have that. So this is another very interesting system that create engineer-based heterostructures to again increment the absorption site for catalyst materials. And this is something that we did. So we used again two of the systems, so tungsten and molybdenum oxide nanowires. We reduced graphene for hydrogen evolution reaction. That was a very interesting piece of work. So we did hydrothermal synthesis. This is a certain temperature and pressure just to annihilate and have the system ready. We did also a sophisticated construction of palladium and lead, just alloy nanocubes, again as a robust hydrogen evolution reaction system. We use here certain chemicals, like for example CTAP, so it's cetyl tritamethylammonium bromide, and TIPTA, tetra and butylammonium bromide and tetra ammonium chloride. So that particular system helped to create the nanocubes that we were referring here. We go also looking at silver, platinum, silver nanodendrite. So this is another similar type of work, like the nanocubes. We use also ascorbic acid and silver nitrate. Yes, we obtain a catalytic effect, so a large surface area. So that's what we need. We want a large surface area to increase the absorption dissorption spaces, and then will be a good electrocatalyst. We use also other type of materials like ordered mesoporous carbon for, and then we were looking at with cobalt and phthalocyanine. Okay, so and this is again catalytic effect for hydrogen evolution reaction. So some of the conclusions we mentioned about platinum and how we can or try to reduce the number of metals into the systems. The only problem we said is the critical raw materials. So we have tried to combine with different materials, and in particular to look for also carbon and nitrogen based compounds. Okay, so this is, we have seen several examples. We have seen graphene, we have seen graphite, and different carbon based materials. We have seen also the hydrogen evolution reaction performance of the biometal. We said it was attributed to the synergistic interaction between the both metals or the bimetallic metals. Some of the barriers to the implementation that we have seen already. So this is, although some of the work are quite interesting, to market that research or those research into something that is feasible and sustainable, it might take 20 to 30 years. At the moment, obviously, one of the issues hydrogen use view with trepidation by the public. So how to transport, how to store due to the high flammability. There are obviously ways like using carriers such as methane or ammonia. Current hydrogen production cost is higher than conventional fuels, as we mentioned earlier on in that particular paper, compared to, for example, reforming or the steaming, which is obviously at the moment one of the cheapest. But as we mentioned, is the high production of CO2 and CO. Technological, numerotechnical challenges. So there are obviously the critical raw material that we mentioned, limited industry interest and investment in research and development. More and more, we need to find more sustainable materials that can come from, for example, bio waste or food waste to produce carbon-based materials. But the problem is, again, we need the catalyst. So one of the ideas will be obviously to couple hydrogen energies with other energies, such as, for example, batteries or solar. But one of the things very interesting, I was looking at the news, and one of the things is, what about if we have a metal instead of a gas? So imagine how much it will help us to carry the gas, to carry hydrogen everywhere and every household. This is not that far off. So there is already an article, the race to turn gassy hydrogen into solid metal. So this is something that is already done. So hydrogen using a diamond anvil cell to exert pressures in excess of 3.5 million atmosphere and resistively heated to a temperature of 475 Kelvin. At the moment, obviously, the conditions are very harsh, very difficult to mimic in real life, but there is some light at the end of the tunnel with renewables and also with bio waste materials to produce better catalyst. Okay, so now some of the acknowledgement, it goes into the research committee, interface, School of Pharmacy, some of the universities I work with, so Janssen University and Ludwig University, obviously National Science Center, School of Pharmacy and Royal Society of Chemistry. And there is also a lot of people behind this work I would like to personally thank. So James, Gemma, Susan, Emily, Graham, Alberto, Linda, Christine, Prabhu, Mandut, Faisal, and the staff, 1601, 1604, and Vinus Rajendra, he was done quite a lot of work on green hydrogen, and the admin. So thank you so much, all of you, for your listening. Thank you.
Many thanks, Carlos. That's very interesting and very interactive presentation. Very exciting. I don't know if I've not seen many questions, but if you do have questions, please shoot it out. Maybe as the questions come through, if you've got a question, you can raise your hand or you can type it in the chat and I'll pick that up as we go ahead. You mentioned limited investment. What can we do about that?
Yeah, very interesting question. I think one of the things is obviously when there is a new technology coming or the new thing, humans, we are a little bit apprehensive to take new things, new aspects and new energies. So I think this will change over the years. I think hydrogen has a lot of opportunities. It's a fantastic alternative of energy. But one of the things that I said, and I think is obviously key, is to couple hydrogen with other energies that we already have.
Okay. and can see somebody typing. But as we wait for that question, maybe the next question I can ask is, most of the solutions you propose for catalysts, they are metal-based. And most of them, as you rightly identified, also they are rare earth metals. Are there potential for other type of catalysts coming up there, as clay-based, silica, polymer, bio, etc.? Are there other options we could probably look in the long run?
Yes, yes, indeed, yes. There are obviously all the materials that I show you in that particular table, but many of them, they're coming under the critical raw materials. So for example, silica is quite interesting. The metals are key. Conductive polymers perhaps in the future. And we also have seen obviously liquid crystal, metallic liquid crystal. This is something quite interesting. Some of the colleagues are working on that, creating better catalysts. One of the important aspects about the catalyst is just to have a large surface area that graphite and graphene offers, that a large surface area with many absorption, desorption points. This is what the catalyst needs, but also need the metallic aspect. So obviously it can be embedded into, as you mentioned, obviously a polymer or other type of, let's say, carrier. That will be obviously fantastic.
Brilliant. Thanks for that. We got a question or comment from somebody, TI. Top-notch presentation. Thanks very much for intriguing message about turning hydrogen into metal. Can you talk more about it? What's the goal? What's the TR, etc.? Something you can help?
Yes, obviously the metal hydrogen is I guess it could be obviously something about in the future. I think it's a fantastic, especially avoiding all the issues that we have at the moment, how to transport hydrogen, flammability because of a gas, etc. So obviously we have a metal hydrogen. It will be fantastic. It will be fantastic because I think catalyst will be reduced. We have a metal system, but at the moment, as I mentioned, and the article mentions, the pressure and the temperature are obviously not to our reach. But I'm guessing that could be sorted perhaps with better reactors, better conditions, etc. So this is something the same with pyrolysis, for example. There are alternative methods like hydrothermal carbonization. This is a method to use less energy, less pressure under a very tight container reactor. So this perhaps is something that if we could design that, then it will make a difference.
Oh, wow, sounds very exciting. There's another comment and maybe a question as well from Finnoth. So the question is, thanks, Carol, for the nice presentation. How to really control the synthesis process to have isolated single atoms, as it tends to aggregate quickly. How about the stability of a single atom catalyst during electrolytic water splitting reaction? Is that possible, or a viable solution?
This is obviously a very, very, very interesting question. So thank you so much. A single atom, yes, that would be obviously the future. There are already articles, there are prototypes and research. The universities looking at that in the single atom. It would be the future, as I said, but it will take perhaps 20 to 30 years to get into where we want to be.
Okay, that's great. And maybe you can ask a general question or maybe a comment. Maybe as we wait for one more to come. What inspires you into this area? Why are you doing and this research and excited in catalytic materials? And what do we do to get more people like you up here?
I think it's something. Obviously, we want to have a circular economy. We want to try to avoid so much waste that we have at the moment. All the waste that we are generating, convert that into something viable and very useful. At the moment, for example, say plastic is thrown away. There are some interesting projects with reactors and looking at the plastic converting into oils, and that oils could be used as a catalyst and other type of materials or fuels. So that is obviously something fascinating. It's something that I always like, because I don't like things that we don't like. I feel sad for things that it seems that, oh, we don't like them anymore, let's throw them. I feel sad. I feel sad because I get inside a plastic bottle. It seems to be crazy. I get inside into a plastic bottle and I feel sad for the plastic bottle to be in the bin and not to be reused. So it's the same with everything that we do. So everywhere we go, we walk around the streets, a TV throwing, everything we throw away. And I would like to convert those material into something suitable. So that's what I think.
Okay. Well, with that comment and the advice for the future, and thanks very much for the presentation, for encouraging us not to go into a throwaway culture. And to our audience for listening, thanks very much for us and being with us. There will be another Celis event which will be coming up in at the end of the month. And with that, and from me, from our colleagues, Gemma, who is an organizer, thanks very much, and look forward to see you again. Bye for now.
Thank you so much. Thank you, everyone.